Hi everyone! Welcome to this video on proof by induction. If you want to learn about proof by contradiction, you'll have to go and watch Matt's video. But today we're going to be learning about proof by induction. We're going to be going over an example, and we're going to be learning about what you're required to know for the exam. So let's get started. So first of all, what is proof by induction? Proof by induction is a method of proving correctness, and it uses inductive reasoning. So it makes a conclusion or an inductive step based on past behavior. So I've got some examples here. Which of these steps are the inductive step in our inductive reasoning? So in this first one, if Matt enjoys Italian food, if Matt enjoys all Italian food,
You know, I really love Italian food.
and Italian food includes pizza, then Matt must enjoy pizza. If that's the case, which of that's the inductive step? And if Ches faces the 78 tram, and the 78 tram runs on Chapel Street, then Ches must be on Chapel Street. So in both of these examples, we know that the third step is the inductive step, because that's when it's making that leap of logic. So, George's foolproof step-by-step guide to understanding proof by induction. Step 1. This includes stating that the algorithm works correctly and what we are trying to prove. So we need to explain a little bit about what the algorithm is meant to do so that we know what we're actually proving. Step 2. Show that the base case of the algorithm is correct. So in this case, it's P of 1, or whatever the algorithm is of 1, and we're just trying to say that this one is correct. And we can do a bit of explaining for how we get there. And then step 3, we're assuming that P of k is for the algorithm is correct. So we're making an assumption here, and then on step 4, we're going to say, this is our inductive step, that if P of 1 and P of k are correct, then P of k plus 1 must be correct. And we can explain how this is true by explaining how the algorithm works, and this is our inductive step, so it's a very important step. And then finally, we've got step 5, which is a bonus step where we're explaining when the algorithm will terminate correctly with the correct solution. So for example, if this is an iterative algorithm, we can explain where the base case is, or this is a case-by-case thing, so we need to explain when it will stop and terminate with the correct solution. And the PageRank algorithm, we need to know the correctness for all of that, and correctness and limitations for all of that. We also need to know the inductive and contradiction methods for demonstrating the correctness of both simple, iterative, and recursive algorithms. So as much fun as it would be memorizing how we can prove all of these algorithms just off the top of our heads so that we can get that written out on the exam, we also need to prove simple algorithms that they'll give us off the bat. Therefore, we need to understand how the proofs work and not just rote learn them. So today we're actually going to be doing that. We're going to be learning how to do a simple algorithm. So let's prove a simple algorithm. So we're going to do this algorithm, which is our algorithm frequency, and we're going to use George's foolproof step-by-step guide to prove that it works. So let's start with a very simple algorithm that we're just going to run through and see how this works. So this is our algorithm called frequency. And what we need to do is understand how it works, and we're just doing step 1, which is stating the proposition that the algorithm works correctly. So when we have a look at this algorithm, we need to understand what we're trying to prove, and therefore what the algorithm does. And we can infer this from the name, or we can do a trace, or we might have some more information given to us. In this case, we know that it's an algorithm that's counting how many of one thing is in a list, and it's just going to return a frequency at the end. So in this case, we can write for step 1, the algorithm frequency will count how many times a given value appears in the list, and this is the proposition that we're trying to prove. So let's move on to step 2. Now in step 2, we're showing that the base case is correct, so that's P of 1. And we're going to do this, we need to first figure out what the base case is. And this is actually something that you can really struggle with. So it can be quite difficult for students to understand it on a case-to-case. Hopefully you get a nice and easy algorithm on the exam where it's very easy. In this case, we're going to say that our base case is a list of one item. So for this algorithm, the base case would be a list with just one value, if there's just one value in the list, the value is either going to match the target or it won't. Therefore, it's going to return a 1 or a 0, and therefore the base case will be correct. So we know this because we know how the algorithm works, and we know what it's going to do in this case. And it's sort of, we're just explaining what the algorithm does in this step. That's the main idea of what we're doing. And then we move on to step 3. We're assuming that case K of the algorithm is correct. And this tricks students up a lot because we're making an assumption, and it really is an easy step. There's not that much to it, but it sounds a bit complicated. So the step is quite simple. Let's assume that an input of size K is correct. In this case, we can assume that the input of size K will return a correct result. So it's just an assumption that we have to make. And then that brings us on to step 4. And step 4 is our inductive step, as we know. So we're saying that if P of 1 is correct, as we know, and P of K is correct, which we've just assumed, then K plus 1 must be correct. And we just need to explain how the algorithm works to come to this conclusion. So as we know that a list of length K is correct, adding an additional element to this list will either increase the count by 1 if it is equal to the target, or it will stay the same. And this produces a correct result. Therefore, the algorithm correctly identifies the number of elements that equal the target in the list, proving the algorithm. So what have we really said here? We've said that because we know that K input is going to be correct based on the assumption that we made before, and we know that 1's going to be correct because we know how the algorithm works, and we just explain what's going to happen when we add one more item to the list, which is really the same as what we explained in step 2. Therefore, we know the algorithm is going to work. And this is the hardest step, but I think you all have it because it's just adding the other steps together, really. And then step 5, we need to explain how the algorithm is going to terminate with the correct solution. So this is a very important additional step to keep in mind. As we have proved that the algorithm produces the correct result, we also need to prove that it will know what to do once it has found this correct result. So the algorithm will go through every element in the list using a loop, and then once complete, it will return the total. Therefore, the algorithm will terminate with the correct solution. So in this case, we can explain it that way because it's using for I in list, that once it finishes every element in the list, it finishes. So that's great for an iterative algorithm. If it's a recursive algorithm, we need to explain what happens at the base case of the algorithm, that it will return it correctly. It's a very simple step. We just need to explain that, and then we're good. So let's put this all together. For the algorithm we have of function frequency, the algorithm frequency will count how many times a given value appears in a list. This is step 1. And then if there is just one value in the list, the value will either match the target or won't, therefore returning 1 or 0. Therefore, a base case will be correct. Let's assume that a list of size K will return a correct result. Since we know that a list of size K is correct, adding an additional element to the list will either increase the count by 1 if it is equal to the target, or it will stay the same, and this produces a correct result. Therefore, the algorithm correctly identifies the number of elements that are equal to the target on the list. And finally, we know that it will go through every element in the list using a for loop, and once complete, it will return the total. Therefore, the algorithm will terminate with the correct solution. And this is our proof for the function frequency. And now that we've done all of that, I think everyone watching this video will understand how this works. And it comes together really, we're just following the steps, and we just write out the step, and we should come with the correct solution. Now I hope everyone's learned something from this, and they're able to apply this to their own simple algorithms. And if you need help with any of the more complex algorithm proofs, then you can always access that on the LMS. And if you want to learn about proof by contradiction, then you need to go watch Matt's video. Hope everyone enjoyed. Goodbye.